This is lesson 14.1, fitting exponential functions to data. In this lesson, the goal is to be able to represent and interpret categorically and quantitative data based on two variables. What we're pretty much going to be doing is we're going to be given data through a table, x, y table or x, f of x table, and then we're going to be asked to create an exponential function equation from the table. So let me just kind of walk you through some examples of tables that are exponential and examples of tables that are not exponential. If we look at example A on page 46, notice we have 0, 1, 1, 4, 2, 16, 3, 64, and 4, 256. For something to be exponential, the ratio of the second y divided by the first y has to equal the same for each ratio. So f of 1 over f of 0, so 4 divided by 1 is 4. 16 divided by 4 is 4. 64 divided by 16 is 4. And 256 divided by 64 is 4. So if all are equal to the same number, that's a good indication that this table is an exponential. It creates an exponential graph. Versus if we were to compare some other tables, let's look at B. If we find the ratio of the first two, so 7 divided by 1 is 7, but then when we do the second two, 13 divided by 7, that is not 7. And 19 divided by 13, that is not 7. So this is an example of something that is not exponential. So for something to be exponential, they need to equal the same value. Okay, so if we were given a table, our goal is to determine what a and b are in this exponential function equation. So let's go back to this example. Let's start with a. How do we determine what a is? Well, a is actually the first number when x is equal to 0. So when x is equal to 0, f of x is equal to a. So a is equal to 1. Next, to find b, this is where we're going to be doing the ratio. So to find b, we're taking the ratio of f1 over f0, f2 over f1, and so on. And we need a common ratio for this to be exponential. And just like how we saw in the part A example, the common ratio was 4. So I wrote it up here. So again, 4 divided by 1 is 4, 4, 4, 4. So since the common ratio is 4, b is 4. Now putting this together, we have f of x is equal to 1 times 4 to the x power, which becomes f of x is equal to 4 to the x power. And we have our equation right there. Next example. So let's look at this example. We have these points. The first thing that we want to find out is what is a. So a, remember, is when x is 0, a is f of x. So f of 0 pretty much. So a is equal to 4. Next, to find b, we need to check to see if the ratios are equal to each other. So I'm not going to test all of them, but I'm going to test a few. Let's do f of 1 divided by f of 0. So 1 divided by 4 is 0.25. And then f of 2 divided by f of 1. So 0.25 divided by 1 is 0.25. Notice that these are the same value, and because these are the same value, that's my common ratio. So b is equal to 0.25. And if I was to write 0.25 as a fraction, it would be 1 over 4. So my function would be f of x is equal to 4 times 1 over 4 to the x power. So a and then b. So let's actually look at an example, if there is some. Actually, there is no examples for you to try in this part. Okay. So in the real world, when you collect data, or when data is collected, sometimes it does not fit a model perfectly. So sometimes the common ratio is not the same. If you pick 2 points, you will not find the common ratio equal to each other. So if that's the case, we could actually find the exponential function manually, or we could use a tool called exponential regression tool, which is on a calculator or on Desmos. I'm going to kind of walk you through how to do it manually. So we're not going to actually do a problem, but I'm just going to show you that we can do this manually. It does take a lot of work. And then I'm going to show you how to use the exponential regression tool, which is on a website that I'm going to give you in a little bit. Okay, so let's look at an example here. So let's say that we have this data here. We have weeks 0 through 9, and we have revenue. And we know that A is equal to 95.3 because when x is 0, that's what A is. So we know what A is. But what happens when we're trying to find B? When we are trying to find the common ratio, remember that we divide the second y divided by the first y, the third y divided by the second y, and then we have all these values. So doing all that, we have 0.59, 0.42, 0.69, 0.54, 0.55, 0.69, 0.58, 0.58, 0.55. Now notice that a majority of these numbers are all different, but they are similar in that they're close to a certain number. And we could actually find that number by taking the average of all of these. And remember, to take the average of something, you count, or you take the sum of all these values and divide by the total number of values. So because there were 9 numbers, and then there was 9 numbers, we add the 9 numbers and divide by 9, and then we get the average, which is 0.58. So this is the average common ratio, and that is going to be the B term. So when you're creating an approximate model for this exponential function, A is 95.3 and then B is 0.58. So again, we're not going to go into doing this manually. You guys do have the option to do it below, but just know that we're not going to be doing it. We're going to actually rely on the exponential regression tool, which starts on page 49. Okay, so the exponential regression tool is a tool that we could use to plot data points and to model a perfect fit exponential function. There are a couple of things that we need to know before we use this tool. One thing is that we use statistics. You guys do not need to worry about the statistics, but one thing that we're going to be talking about is something called the coefficient of determination, which is r squared. So the coefficient of determination, when this value is close to 1, that means that the function fits the exponential data. And we're going to see that when we do the scatter plot in a little bit. Then with this tool, it actually also gives us A and B. So all we really need to know is how do we use this tool, how do we plot the values, and then we could get this information. We could get the coefficient of determination, we could get A, and then we could get B. So let's actually do that. And what we're going to be using is we're going to be using this this table here. So actually this table is connected to this table. It's just in two pieces, but it goes from 0 to 10, and then these are the y values. So let me actually switch to Desmos, or actually let me switch to the website that we're going to be using. So you're going to go to bit.ly/L for L math. So capital L for capital L math. And then you're going to go to Algebra 2A. And you're going to go to the exponential regression model. And that's going to give us a shortcut to Desmos. And this is an example of one that was created. So you see how we have X and Y table here, and all data was plotted. So you could actually, put in your own numbers in this table, and you get a point here. Then if you scroll below, you're going to see a couple things. So the first thing you're going to see is the coefficient of determination, which is 0.9933, and that is really close to 1. So because the coefficient of determination is pretty much 1, these points, they form an exponential graph. And then we could also see the parameters. So we could also see what A is, and we could also see what B is. But this is not the problem that we have. So remember that the problem that we have, we had different values, and I actually took the time to plot those values on a separate window. So from 0 to 10, and then we have 3.93 all the way up to 62.98. So then we look at the graph. So each of these orange points, or the points that we plotted, and if you look at the graph, it looks like most of these points are on that exponential graph. So now let's scroll down and let's look to see what the coefficient of determination is. And it is 0.9975, which is really close to 1, which is really good. This means that these points fit an exponential model. And then let's look to see what A is and what B is. So A is 4.77, B is 1.297 if I round that. And we're going to use those values on the next page, on page 50, to create our equation. So again, the coefficient of determination was 0.9975. A is 4.77. And B is, I'll just round that to 1.30. Okay, so let me go back. Okay, so now we're going to write our equation. And our equation is going to be y is equal to 4.77 times 1.30 to the x power. So this is A and this is B. Okay, and that completes this example. So again, if we're given a table, we could use the regression tool. And then again, the website was bit.ly/L dot ly slash capital L for capital L, capital M math. Okay, and then we're going to actually not do this problem, so let's skip this problem. And then we're going to go into the next section. The last part of this lesson is solving a real-world problem using a fitted exponential function. Okay, so in the real world, there are situations that occur that require a mathematical model to look at trends or patterns, or to make predictions based on decisions from the data. So let's look at one example. The Texas population increased from 20.85 million to 25.15 million from 2000 to 2010. Assuming exponential growth during the period, determine the exponential function where x equals 0 represents the year 2000 and x equals 1 represents the year 2010. And we're going to use the f of x equals a times b to the x equation to do this. So let me kind of show you my notes on this. So in the year 2000, we have 20.85 million. In the year 2010, we have 25.15 million. And what they're telling us to say or to do is the year 2000 is x equals 0, and the year 2010 is x equals 1. So pretty much this transfers into an x and y graph like this. And the first step in finding a or b is actually to find a. To find a, we're going to use this function formula, f of x equals a times b to the x power. And then we're going to plug in the first point. So we're going to plug in 0 for x, and we're going to plug in 20.85 for f of x. Doing that gives us a equals 20.85. Because remember, b to the 0 power becomes 1. So that goes away. Next, we're going to find b by looking at the second point, which is 1, 25.5. And then also knowing that a is 20.85, we're going to be using this equation. So f of x equals 20.85 times b to the x. So f of x is 25.5, so we plug that in there. X is 1, we plug that in there. B to the first power is b, and b times 20.85 is 20.85b. To solve for b, I could divide both sides by 20.85, and then these cancel out. And I'm left with b equal to 1.206. And then we have our function. F of x is equal to 20.85 times 1.206 to the x power. So this is a, and this is b. Okay, so now let's try one example similar to this. Remember, our goal is to find the function equation. So at the bottom of page 51, the number of fish in a certain pond started at 2.12 thousand. After a year, the number of fish decreased to 1.96 thousand. Determine the exponential function that would determine the number of fish in the pond after t years. So we're basing it off this equation right here. F of x is equal to a times b to the x power. Because they do talk about time, instead of calling this f of x, I'm just going to call it f of t equals a times b to the t power, or where t stands for years. Then I'm going to create a quick table. So an x and a f of, a t and a f of t table. So in year 0, there are 2.12 thousand fish. In year 1, there is 1.96 fish. 1.96 thousand. So we're going to find a first by plugging in f of t and t into this equation. And we're going to get 2.12 is equal to a times b to the 0. And that becomes 2.12 is equal to a times 1. So a is equal to 2.12. Then I'm going to create an equation with a. So I'm going to write f of t is equal to 2.12 times b to the x power. To the t power. And I'm going to plug in the second point. So I'm going to plug in t is 1 and f of t is 1.96. So 1.96 is equal to 2.12 times b to the first power. So that gives me 1.96 equals 2.12b. And then I would divide both sides by 2.12. So b would equal 1.96 divided by 2.12, 0.92. And then we could write our function equation on the side here. So f of t is equal to 2.12 times 0.92 to the t power. Okay, class, so that pretty much ends lesson 14.1. So you are going to have a few homework problems where you are going to have to find the exponential function equation from data. You are going to have problems where you are going to have to use the exponential regression tool. And the checkpoint is similar in that way. So yeah, let me know if you have any questions on the homework or checkpoint, or if you just need any or more understanding on certain parts of this lesson. Please comment on the video link that I sent. So when I post the video, you could comment underneath, and if you have any questions on Google Classroom, please type them in. All right, so have a good day, guys.